We took a quick look at switches and how they work, and in this video we will take a look at routers and network interface cards and how they work. So to review how we think about routers, remember that routers operate at the network layer, the OSI network layer, layer 3. They work with packets. We use routers to connect two separate LANs to form an inner network. And things like broadcast frames, although broadcast frames are sent out by switches, they are not forwarded to beyond broadcast domain. So routers are what connect a broadcast domain to something else, but routers will not forward broadcast frames. So essentially what that says is that when you have a router connecting two LANs, the broadcasts stay inside those LANs. The routers will not forward any broadcasts. So routers can be used to create a very complex set of internetworks, and actually the entire internet is actually just a whole bunch of LANs that are connected together. Of course, there's a lot more to it than that, but that's at layer 3. That's all it is you have a whole bunch of LANs, and then you use routers to connect them up into one big giant internet. But the nice thing about routers is that you can use routers to have multiple paths between a source and its destination, so that if one path goes down for whatever reason, some machine or a router goes down, you can reroute and create what's called a fault tolerant path. So you can have fault tolerance, you can have load sharing, so you can have different paths that will allow you to send data in parallel on multiple paths, things like that. And that's what the internet was designed to do. Okay, so features of routers. There's types of routing that depends on the features of routers. You have each router has to have pretty much at least one interface. Two or more is what you want to for a router to be useful. Each router, just like, well, not just like, but similar to the way switches have switching tables, routers have routing tables, which are actually quite a bit more complicated, and we'll take a look at what routing tables are like. There are different routing protocols. There are routers that will control access of certain networks. For example, let's say router H has some access control list, which might say that only traffic from a particular set of IP addresses or subnet can enter network 8. You can have access control lists like that, rules that says, okay, only certain packets can leave network 8, let's say, for example, and only certain source IP address can get through to network 8. So there's all kinds of complicated things. We probably actually won't look at things like access control lists. We'll take a quick look at routing protocols. You'll see that in the lab as well. But mainly we're interested in router interfaces and routing tables. Okay, so a router with just one interface will not accomplish anything. You have to have at least two. So at least, well, one doesn't do anything, so at least two. Two or more is what you want. And typically, a lot of routers have just two interfaces. But in the book, we will consider the more, in the book, it considers the more general case where routers have more than two interfaces. So I'll scroll back up, take an example. This router has only two interfaces. This router has two. And I forgot to mention that this is how we represent local area networks. Sorry, I didn't mention that, but this is a very simplified diagram in which we sort of ignore the switch. So this straight line here is sort of an old way of representing a bus, or and then we use it for switches. So this router is connected to a LAN over here, network 8. it's connected to another LAN of routers. So this switch connects router I, router H, router E, and router D. So this is a network 7 that connects 4 routers together. Also, you can have routers connected directly to another router. And remember that these two interfaces are going to be like interfaces, and so you need a crossover cable to connect router E to router D directly. Whereas these are switches, so you can use straight through cables from routers. Also notice that this router E has 3 interfaces, one going to network 7, one going to this router D, and it actually is a subnet. This connection between these two routers is network 3. It's actually a subnetwork. And then router D has also 3 connections, one going to router E, one going to network 7, the switch, and another one going directly to router 8, which is also a network or subnet. Router A has 2 connections, one going to a switch which has 2 other routers connected to it. And that's about it. These routers, I'm just quickly scanning, they either have 2 connections. Like router B is not, it's shown to only be connected to one network, but chances are there's another interface that makes router B useful. If it only has one, at least it has one, but it doesn't do anything if you have just one interface. You have to have router B connected to something else to make it useful. Router 2 has 2, router A has 2, router C has 2, router G has 2, router F has 2. Yep, so the most complicated routers are D and E with 3 interfaces each. Okay, so routers must have 2 or more in order to be able to forward packets, to be useful, to be able to work as a router. You have to have 2 or more. So here's what routers do. Just like when switches get a frame, it decides where to send that frame. When a router receives a frame, it receives it on a certain interface, and it compares. Just like with any LAN station, first of all, it checks the destination MAC address of that frame, so that's working in layer 2. Compares that with the MAC address of that router interface. If it's a match, that means that frame was destined for that router's interface. So in a local area network, if a LAN station gets a frame with that destination, it just sort of says, okay, this is for me, I'm taking it. However, routers have to do more. If it gets a frame where the destination MAC address matches that interface's MAC address, it only means that it's being sent to the router. It might actually have to do more work with that frame. What it'll do is the router basically peeks inside that frame. So it takes away the frame header trailer. Of course, it checks, the checksum and all that. And as long as that check out, you get rid of the frame header and frame trailer. You look at the packet inside the frame, and then you look at the destination IP address. This destination IP address is the thing that tells the router where to send that packet inside that frame that just came in. So there are a number of possibilities. The easiest possibility is that someone is trying to contact the router directly through the interface. So in that case, the IP address in the packet that came inside the frame will match the router's IP address. And so it says, okay, this IP address is same as mine, so this packet is destined for me, and it just consumes that packet. It says, okay, this is for me, I'm not going to send it anywhere. Usually what happens, and this is the main reason for using routers, is that the IP address will be of a totally different network. That is, the IP address won't match the IP address of that router interface. And that's usually what a router has to handle. But then what the router has to do, just like switches consult their switching tables, the router consults its routing table to figure out how to get that packet to its ultimate destination. So routers only know which other routers are connected to it. It does not know the ultimate path that this packet will take. All it knows, all a router knows, is what other routers are connected to which interfaces. There are similarities with switches, but routers are more complicated. Okay, so once it figures out, okay, I got this frame, I looked inside, I got a packet, the destination IP address is not mine. Now I have to use my routing table to send that packet out one of its interfaces, one of its other interfaces, not the one that it came in on. You can never send a packet out the same interface that it came in on. If you do that, that means there's a chance that you can get like an infinite loop of packets going from one router to another and back and so on. That's something that would be an error condition. It does happen, but that's a sign that something was misconfigured. Ordinarily, you get a packet inside a frame coming in on one interface. You open up that frame, look at the packet, decide which of the other interfaces you will send that packet out on in a new frame. That's called packet forwarding. I hope you that makes sense, because this one slide basically captures everything that the router has to do, pretty much, or the main things. Okay, so there are a number of routing protocols. So a routing protocol is just a way of setting up routers so that you can set up paths that will work for any machine on that network to any LAN station to get their packets out to their destination. So a set of rules that routers use to exchange information, and routers are set up so that they can all use different routing protocols, but it'll still work. And so the main reason for that is routers are really just computers. They're running programs, and so they're running programs that follow certain routing protocols. So there are two main types of routing protocols. The distance vector protocols. An example of this would be RIP, Routing Information Protocol. And another main type of routing protocols is link state protocols. An example of that is Open Shortest Path First, OSPF. Okay, so these are the two main kinds of protocols that we will run across. You actually won't do a whole lot with this, and you will see how routers can implement either one of these protocols internally. Okay, so before we get onto network interface cards, let's take a quick look at wireless routers and access points. And so we'll take a look at Wi-Fi as well, and then we'll come back to network interface cards. A wireless router is actually three devices in one. A wireless access point, that is, it's got an antenna that nearby LAN stations will connect with using air as the medium, and so that antenna will receive signals, electromagnetic radiation, that's sent out by LAN stations, and that it can send to LAN stations as well. It also has, in addition to that access point, it also has internally a router, and it has a switch. So it actually is a number of things put together. That's what makes it complicated. We don't do a whole lot with wireless routers because it is complicated, but we do realize that that is how most people connect to the internet, is through wireless machines. So we'll just have a quick overview of how they work. Turns out the main ideas are not that different from Ethernet networks. Of course, physically they have a totally different medium. They don't have wires, so they're wireless. But all the protocols sort of work the same way, and it's just for when you're learning, it's much easier to use a wired setting. So some of the basic wireless settings on most access points, when you go into a cafe, what you will see is on your phone or your laptop, on your wireless device, you will see an SSID, wireless network name, and then you say, okay, I want to connect to this wireless network name. It also has different actual Wi-Fi protocols that you can use. So typically you can use 802.11 something, and there's been a whole bunch of different standards. It turns out the first one was 802.11b. So remember, in case you forgot, 802 is the IEEE networking set of protocols. 802.11 means wireless, or it's under the marketing name of Wi-Fi. The very first one was 802.11b, which was way back in 1999, and it was not very fast. It used a band in the 2.4 gigahertz spectrum, area of the spectrum, and then after that came 802.11a. The letters don't really tell you. It doesn't go ABCD, unfortunately, for various reasons. So that also came out about the same time as 802.11a, and it was used a higher frequency spectrum, and it allowed you to have Wi-Fi connections going 5 times faster, it turned out. Then came 802.11g, and a few years later it wasn't a huge improvement, but then one of the big improvements came with 802.11n. It was about 10 years ago, and the nice thing about 802.11n was that it allowed both 2 and 5 gigahertz bands, and so it could do simultaneous transmission as well. And then came 802.11ac, which is normally that's about when you buy new equipment. And if you check your phone, chances are you're using 802.11ac right now when this video is made. And the next generation is 802.11ax, or it's actually being marketed as Wi-Fi 6. And so it's out now, but personally I have not seen a lot of machines that use this protocol 802.11x. It's very fast, not a huge step up from 802.11ac. If you have 802.11ac, there's not much reason to get Wi-Fi 6 right now. Okay, so there are different Wi-Fi protocols. Your wireless network name, or SSID, may not reflect what that network is using. You don't always know. Usually your devices are capable of certain sub protocols, like 802.11 maybe G but not AC, or AC but not yet AX, and so on. No. Okay, typically you get access point with a default SSID, which you probably want to change. Like you might get an SSID like Netgear, and of course if you look around with a smartphone or laptop, you'll probably see a ton of Netgear SSIDs, and so the recommendation is that you change it when you set it up. So each one of these bands will have multiple channels, and in the US, I believe, we use a certain number of them. I forgot which ones, but 1, 6, and 11 definitely work in the US. In Japan, they use a different set of channels. And so typically it's recommended that you use channels that are 5 apart. These are different points in the frequency spectrum of whichever band you're using. So 1 and then 5 channels, 5 channels between 1 and the next channel that you can use reliably would be you add 5, you get 6, and then add 5 again, you get 11, and those are the 3 ones you want to use, and you end up using channel hopping. When you send out packets, you'll use different sequences. That's the idea of wireless channels. And that way you can avoid things like collisions, and because you're all in a certain access point, all the machines that are nearby are sharing these channels, and so you'll hop on different channels and send messages in different channels. Okay, you can also have the broadcast status for a single AP access point, and so by default access points are configured to transmit the SSID, so that if you have a AP or access point set up and a wireless device comes in, it can send what's called a probe request, and SSIDs will also broadcast saying that here is my SSID. If you want to connect, send me a message. You can also turn that off, and so more and more people are doing that. You can make your access point a hidden access point, and that is actually the recommendation on it, so that if you don't have people like walking by your house or your apartment and trying to figure out what networks are in the area, stuff like that. Okay. So for security, you do a bunch of things, including hiding your SSID. You can do that, but usual security precautions are to use encryption. It's right now some of the more common thing to do is to use no encryption, or there are still networks that do that, or it turns out about half of all Wi-Fi networks use this old protocol called WEP, Wired Equivalent Privacy, which is actually broken. So you can like decrypt messages that are encrypted using the WEP protocol. Then came Wi-Fi Protected Access, WPA or WPA1, which didn't require huge amount of hardware changes, but this is also broken. So these are ones you don't want to use, although it's estimated that maybe half of Wi-Fi networks still use these broken encryption schemes. You really should use encryption, and it's recommended that you use WPA2, Wi-Fi Protected Access 2. And as of now, there is WPA3, which I have not encountered so far, and I don't know if there are a lot of devices that use WPA3, but it's available. But so far, until there's enough devices that can support this, probably won't see it for maybe in the next year or two. You might start seeing WPA3. So you should use one of these. Right now, at this very moment, WPA2 is still good. It can be broken, and that's why it's about 15 years old, and that's enough time for people to figure out weaknesses, and it held up pretty well. But now WPA2 is sort of not the latest one. Okay, so that's encryption. You definitely want to use the highest level of security for your systems, and so remember that all devices must use that same protocol when you have that encryption scheme. You also want to use authentication. That is, you want a username and password to be able to log into an access point, or to get inside that access point network. You can use MAC filtering. You can say, okay, I know the MAC addresses of all my friends' devices, and so here are the MAC addresses of all my friends. And on campus we use that. Our networks restrict you to using certain devices whose MAC addresses are actually known, because you authenticate one time in the very beginning, and basically what happens is the access points get your MAC address in that procedure. You also want to do things like access point isolation, sort of like we segment wired networks. You want to separate virtual networks for each client, and that way you set up virtual networks so that people cannot listen in on your traffic and things like that, and people cannot break into your connection with that access point. So there's a bunch of things that this is pretty much all we're going to really mention of Wi-Fi and wireless security. This is just not a security course. We do have another security course that goes into more of these details. Okay, so now let's move on to network interface cards. What do we know about network interface cards, or NICs as we call them, NICs? A NIC makes a connection between a LAN station, or usually a computer, and the network medium. And so the kind of device that you buy is crucial to the network performance. These days, your computer, when you buy a computer, your computer comes with a NIC, that an Ethernet NIC that's built into the motherboard right now. You can buy a plug-in card, but if your network interface that comes on the motherboard is not fast enough, or you want a faster connection, you can buy a network interface card that comes separately and plug it into something like PCI Express that can support a much higher data transfer rate, 32 gigabytes per second, and then connect that to give yourself a gigabit Ethernet connection. There are older things like PCMCIA, there's USB 3, there's Thunderbolt, so there's a lot of, and Thunderbolt is much better than this. Thunderbolt is probably about getting close to, but not quite, PCIe rates. So PCIe, at least in this table, it looks like that's the best, but Thunderbolt, I believe, is getting pretty close. Okay, so you would use different devices if you want better connections. If you have a built-in motherboard Ethernet connection, that might be limited to, I'm not sure, maybe it's, you can only do, let's say, 533 megabytes per second, which means chances are not that great that you can use it for gigabit Ethernet. And this particular kind of PCI connection is actually on the decline. It's not used much anymore. These days we'll use PCI Express, and that's definitely capable of doing gigabit and maybe even 10 gigabit Ethernet. Okay, so a slow network interface card will limit your network performance, and if your network performance is limited by the hardware, your NIC, then you want to buy a new plug-in card. When you select a NIC to buy, you want to check out those physical characteristics and make sure that you can plug it into your PCI Express bus. Make sure you have one. Make sure that the network technology that it's using is compatible with the switch you're using. If you have an older switch, like 100 megabit per second switch, plugging in a gigabit NIC into your computer and connecting to that switch will not help until you update your switch as well. So you want to make sure you understand what your network technology is, and then you want to get the right connector for the media. If it's Ethernet, remember you need to have Cat5 or Cat5e or Cat6 or maybe even Cat7 or Cat8 type cables. So you have to be aware of all of those limitations and features on your network. There are all kinds of nice hardware enhancement options. You can have a shared adapter memory, so that the memory of the entire computer is mapped onto memory in the network interface card itself and the hardware, so that it's very fast access. You can use shared system memory, so that the network interface cards, processors, remember these network interface cards, really it's just a CPU really that is running a program, and that program can be fine-tuned to select some region of RAM on the computer, and pretend that it was its own memory to make data transfers between the system and the NIC faster. So there's all kinds of these hardware features that you can use to enhance the speed of your NIC. There are also things like bus mastering, that is, which allows a network adapter to take control of the computer's bus. So if you have a PCI Express bus, the network adapter could potentially take control of that, which means it can speed up networking, but a downside might be that your graphics might slow down, or some other peripheral input-output peripheral might slow down because your network card has taken control over some of these buses. You can have RAM buffering, like we mentioned. You can have additional memory to have temporary storage in case if you're using a NIC to do a massive file upload or download. So you can use memory, additional memory, to make things faster. Often the limiting part is the network, but if your network's really fast, your network speeds are really high, then you will have to keep up with that data that's going out or coming in. You can have complicated coprocessors that will do things like encryption, for example. These days encryption is pretty much needed, and if you can put that into hardware, yeah, your NIC will be able to process data coming in or going out much more quickly. These days, however, if you look at typical desktop computers, a modern one still uses 100 megabits, and gigabit Ethernet is also actually pretty common, especially for servers. Servers these days, yeah, 1 gigabit per second is considered normal, and it's moving up. If you will find servers these days using 10 gigabit per second Ethernet as well. Okay, so to summarize the two videos, this video and the previous one, we looked at network switches, how they work. They use switching tables. Switching tables are usually pretty simple. There's just one entry for each port, unless you have multiple switches in a single LAN, and in that case you may have more MAC addresses than unique ports. So you may have multiple MAC addresses on a single port in a switch table if you have more than one switch in that LAN. There are switches with advanced features like VLANs, multi-layer capability, that's layer 2 and layer 3, but we won't really talk about that. And then there's also things like port security that we don't really discuss much in this course, but it is available in the book. We took a look at routers, and just like switches have switching tables, routers have routing tables, and they contain destination networks. The next hop, a hop is a jump over a router. So the next hop tells you which router you're going to, what interface on what router. And so you also have metrics like how sort of quote-unquote far away is a router, and that might not be physical distance. It might more likely be the medium that you use. If you use a slow medium, then it would be considered far away because you cannot transmit data very quickly, whereas if you used something like fiber optic, it might be far away, but it would be considered the metric, or the way you measure distance might take that into account and say, okay, this fiber optic cable is going to send data super fast even though it's far away. And then you look at timestamps too, so that you can reconfigure your routing table. Just like switching tables, or routing tables also change dynamically, and these protocols that we use will populate these routing tables dynamically. That is, they'll change with time. So a quick look at access points for wireless networks. We look at what SSIDs are. and channels. We looked at how network interface cards can affect your network performance and how they depend on both the card itself and the thing that you're plugging it into, the PC bus. And we just take a very brief look at how you can have enhanced features like using more memory to buffer data going out or data going in. You can have more complicated co-processors to speed up your network traffic and so on. Alright, so that's it for how these network devices work. Next we will take a look at DHCP.